Thank you very much. Thank you very much for putting together this event. It's indeed very useful, I think, to gather publics working on similar topics, but maybe from different fields, to try to make progress. So what? So is it better?
Oh, we are back to the cube.
I think the cube also resonates a lot.
Is it not possible to you can't turn down the volume of the speaker.
We need the mic to actually transmit to the internet.
Attends, vas-y, fais audio mute, pour voir. Est-ce que... Non, là, il y a aussi beaucoup d'écho.
Là, c'est mieux?
Attends, non. Là, c'est mieux. Okay.
Okay. Oh, okay.
You have to press the audio mute button.
Yeah, but
Can you still hear on Zoom? Okay.
There's some echo, no?
There's still an echo.
Si je parle plus près, il y a moins d'écho, mais c'est très fort. C'est bien? Okay, so I will stay like this. I will be strangled. Okay, not so good. Okay, so what I will tell you about is quite annoying for myself, but I will try to do it anyway. So I will tell you about transport-based generative models and sampling. So I think on the program, no, it's too disturbing for me as well. I just cannot do it.
Okay, maybe like this. You try.
On this?
On this?
No, it doesn't work.
We should accept the invite and go back to the queue.
Okay, we return to the queue.
Is it better? Better.
And okay, if people, I mean, if you're not listening, I mean, it's not if you're because it's really hard at one to be heard in the back, but please don't. I think that's a very simple go in and start technique. Okay.
A low-tech solution.
Yeah. Okay.
Yes. Don't expect me to shout.
Yeah.
I will just do my best. Okay. So in the program, sorry, Grant and myself had very similar titles, so I tried to be more specific in the actual title, where I'm going to talk in particular about those transport-based generative models and sampling, and how we've tried to combine them, how others have tried to combine those ideas, and maybe what's, we are now, finding the difficulties and, what could be good topics for us to discuss to try to go above those difficulties. And what I wanted to start with is to remind ourselves what is a deep generative model, or at least what I will call a generative model in most of this talk. So I make sure we are all on the same page. And a very wide class of generative models that is now used are deep latent generative models. So they are precisely not the ones that Beatrice has just talked about, but they will come in later. And they work the following way. You have a base distribution, something very simple, something you can make your computer sample from in one line of code. And then you have a learnable transformation that involves neural networks, and that allows you to generate some data of interest by just pushing these realizations from the simple base distribution into the learnable transformation. And so with this construction, you define this push forward distribution effectively. And we now know that if you have a smart scheme of training and you have a lot of data to make your training, you can, for example, find a T-theta that makes you transform random Gaussian noise organized on pixels into image of a dog. And this is the example of the score-based diffusion models, but there are different ways of doing it. Now what we are going to be, and something important about this construction is that each time you get a new sample from your base distribution, so a new random image, you get a new image of the dog. And so you have a very effective sampling scheme for those constructions of seemingly very complex data. Now what we are going to be is explicitly interested in are invertible transport maps, so where this T theta is actually constrained to be a diffeomorphism. And the advantage that is coming with this assumption is the fact that this rho theta of x can now be explicitly written using the change of variable formula that is just reminded here. It involves the inverse map and the Jacobian of the map. And if you organize yourself to have parametrizations for T theta and that allows you to compute this inverse map efficiently and the Jacobian efficiently, then you can also compute efficiently. So the actual analytical value of the likelihood of a sample you would have generated or you would be interested in analyzing with this type of models. So I'm not going to go into the details of the training, but just to fix the ideas. You could use different paradigms to train such models. You could use something like a maximum likelihood, and Stefan reminded us about this type of training this morning, as well as score-based objective, which again, Stefan mentioned this morning. But okay, without entering into the details, we know from a lot of data how to generate a model that will eventually be able to regenerate data that looks like the one from the training set. Now, what we will be interested in is actually inference or high-dimensional sampling, I should say, where we have this assumption that was again used, for example, in Gradient stock, where we know target energy function, for example, if I'm thinking of the context of statistical mechanics. And from it, we have a target distribution we want to obtain information about. Or it also happens in Bayesian inference that we have some data that we want to explain with a model that has some parameters. So here X plays the role of the parameters of the model. And we want to consider a posterior Bayesian distribution for the models of the parameter given the data. And so I have a bit these two applications in mind. And I know that doing the direct inference is very costly because it costs exponentially in the dimension. And I want to resort to sampling, which can also be very difficult, of course. This is why we're here. And just to remind what makes it difficult traditionally, it can be dimensionality, could be geometry, could be multimodality. The last one being, in the language sometimes of statistical mechanics, the metastable types of systems. Okay, so this talk, can we use still generative models to speed up sampling as they seemingly are able to sample very complex distribution after they have been trained? Well, just to fix the ideas, consider simple samplers. So for example, consider importance sampling. What does importance sampling do? It relies on a tractable proposal. And it's going, and if I, for example, take as an objective function this bimodal two-dimensional distribution, and here I just plot on the top and on the left, on the right, the marginal distribution, I can, for example, use as a tractable distribution a Gaussian proposal, just unimodal big blob Gaussian. I draw a bunch of samples, and then following the importance sampling scheme, what I will do is compute some weights for each of these samples that are going to put into balance what is the target distribution I'm trying to compute an expectation over compared to what was the density in the proposals that generated the data. And then if I just do that, I change the size of each of the samples I have such that they reflect what is the value of their weights. And I show you what it also gives in terms of marginal histograms if I look at the weighted data. And I recover something that looks like the target. Okay, simple, just a reminder. Although we can here notice that we've thrown a lot of compute away, right? Because there were all those samples in the middle. And of course, they count for nothing in the estimation. And my effective sample size is actually quite low. And I have a lot of variance in my estimation. So it's already not that good, but okay. The conceptual idea is very easy. Other very simple sampler are Markov chain Monte Carlo that relies on local steps. And for example, the metropolis adjusted Langevin kernel is the following one, where you are going to propose to make an update xt plus 1 from a location xt that is just going to be a Gaussian kernel that also follows the gradient of the log of the density, or equivalently the energy that you are interested to sample. And if you do that, you initialize workers in either of the wells. What do you get? Well, something that tells you about what's happening locally in each of the wells. But if you want that samples those quasi-stationary distribution in each of them, but that doesn't tell you about the relative weights of the two modes. Very well, I mean, very classical issues of those very simple samplers. Now, suppose that you can train a model, a deep generative model, such that you obtain a rho theta of x that is very close to your target distribution. And sorry, I was not consistent with my notation, but from now on, my target distribution is going to be rho star of x. So what do you gain? Well, it's quite obvious. So if for the same exact target distribution, I do importance sampling, but this time with a proposal that looks like this. So you have the level sets that are in gray. So it's imperfect. It doesn't look exactly like the target distribution, but you can see that it has a very good overlap with the target distribution. And if I am to draw samples and then reweight them, I will have an estimate that has lower variance. I'm losing less computes, and I can estimate the different weights and have a tractable way of looking at the computing expectations with this type of technology. Same thing for the Markov chain Monte Carlo. And this time you will have on top that you can rely on global proposals. So you can really use your rho theta of x to make the proposals. So this time I have my rho theta, and now I am going to create a Markov chain that really jumps to xt plus 1 independently of xt and gets accepted or rejected according to the Metropolis Hastings criteria. Yes.
There's a gray line between your two wells, and
yes,
this is part of the distribution of the density.
Yes. So this is sorry.
Do you need that?
So you don't need that. That's an artifact actually of the architecture I'm using, and it's actually of the parametrization I'm using. And I don't care so much about it for the reason that it's a very small fraction of the overall mass of my.
It's not the target.
No, I mean my target is the blue one. This is my proposal, rho theta. The gray one. Sorry, it's the contrast is not so great. So the target is still the blue one. So here on the you have the blue histograms and you have in gray the proposal if you want. Yes. No, precisely, you propose and you don't condition at all on the previous step. You just have this, sorry, you have this, if, of course now, PowerPoint. Yes, so, sorry, okay, I pressed, so this gray thing is this rho theta. So it's my surrogate model, and I just use it to propose a new step in a Markov chain. And it's completely global, and I'm just correcting for how much rho theta is not rho star by accepting which is rejecting in the metro. I didn't explain how you obtain rho theta, but it's if suppose you can. and you're totally right. Suppose you can train a model. What do you gain? I think I gain a lot, at least on this two-dimensional example. I might have convinced you that you gain a lot. Now, suppose you can train. That's the first question we need to ask ourselves. How do we train? And second question is, what does it mean to have rho theta approximately equal to rho star? What really is at stake here? So this is two things that we are going to mention in this talk. And suppose you can train is indeed a very central question in this framework, because generative models have been developed to create models that resembles data. So given a lot of data, I do density estimation, I am able to reproduce data. Here, it's not at all what we have. We have is the analytical expression of the target distribution rho star up to a normalization constant. And we want to obtain samples, which would be the data. So we have a chicken and egg problem, in a sense, compared to generative modeling framework. That is the birthplace of the generative models. So how do we do it? So actually, there is a first way of one can think of doing it without data. That is even, I would say, rooted in statistical mechanics, because it's variational methods that is called in the statistic literature variational inference, where what you choose as a learning objective is a Kullback-Leibler divergence, and precisely this one. So the one that is the expectation with respect to your model rho theta of the log of the density of the model and the target distribution. And what you realize when you look at this objective is that you can rewrite it in a tractable way with all the ingredients I provided. So you have your base distribution, you have your transformation from which you can evaluate the Jacobian. You have your target distribution, which you know up to a normalization constant, which doesn't depend on the parameters of your model. And you see that you have something you can evaluate by drawing samples from your base distribution in a non-biased fashion, and you can run a stochastic gradient descent, ascent, I guess, no, descent on this case, to try to find values of T theta that would make your rho theta, so your generative model, resample your target distribution rho star. And if you do this for still this very simple objective, you will see something like this. Say I start from rho theta is this unimodal Gaussian, and I'm going to, so this is, if you want, rho theta zeros, iteration 0 of the gradient descent. And then I optimize this objective function. I will see something like this, where I'm getting rho theta that has a fair overlap with the target distribution. So it has this connection between the two. And I mean, we'll come back to it if you want of why it's there, but in a sense, it would be not too bad of an approximation to then, for example, do importance sampling or MCMC with a proposal that is based on this generative model to get samples from rho star. Okay, but here we are in 2 dimensions, and actually, if I was to initialize my gradient descent with just this, so the same unimodal Gaussian, but that is concentrated and that has not a good, big enough overlap, I would say, with both of the modes, I would see something like this, which is that the model is just going to flow to one of the modes. And once it's there, it has no reason to recover information on the other mode. Because if you look at the way, and one way of convincing yourself that it has to be the case is the fact that when you estimate the loss, you really zoom on where there is mass in your model. So once your model has developed a very good overlap with one of the modes, it has no, I mean, you will almost never sample something that is here. So you will never recover information that something is here. Okay, so this happens here in this 2D picture where I engineer myself to get this mode collapse. But actually, it's something that is even more prominent in high dimension, where it would be really difficult to get a good enough overlap with all the modes you are interested in order to prevent such a phenomenon to happen. And it's really a problem in practice. So this is something that is called, in the jargon of generative modeling, mode collapse, where you concentrate your mass on one of the modes. And I mean, despite this being the case for multimodal distribution, there's been really nice paper written with this type of approach for cases where you are, for example, unimodal distribution. And that's Michael Albergo was one of the first ones to apply it to statistical mechanics. Or there is also the group of Lei, Wang, and Panzong that wrote quite a few papers on this back in 2018, 2019. And it's still a good idea. And you can also try to fix it with annealing. Okay, you can work on it. But something else you could think of doing is actually put yourself within the framework of adaptive MCMC, adaptive Monte Carlo Markov chain. And this is something we're investigating with Brent Foskov and Eric van den Eyden a couple of years ago when I was in NYU doing my postdoc. And the idea is that you can this time go back to, how should I say, the ultimate loss of generative modeling, which is this maximum likelihood. And that actually is equivalent to looking at the KL divergence in the other way, where you have actually an expectation with respect to rho star of the inverse ratio, so of this rho theta of this rho star. And indeed, if you look at it, it's as if given that you were provided samples from rho star, you were just looking so at this maximum likelihood objective, but for which you precisely don't have data. But the idea of the adaptive Monte Carlo is to say, I'm going to run a Monte Carlo and improve the kernel with which I run the Monte Carlo within the sample. And here it would start by say, okay, I'm going to create crappy data to start with by just using a local sampler. So this is what I had showed you before. So I take my simple bimodal objective and I just start walkers in both of the basing and I run a Monte Carlo that is local. I know it's metastable. I know it's not going to recover global information, but still it provides me with some information about the local geometry of each of the modes I might be interested in. And then I can use it to learn a model. The model I'm using on the data that comes from the local MCMC doesn't have the right information about the relative weights, but it still gives me some fair overlap with the target distribution. I can use it then to run some non-local steps, so global steps that are actually only proposing with the model I've learned. And then I can and that will debias the data I get, and I can reuse this data to keep on training. And the idea is to actually do this repeatedly and to converge the procedure. And that will be precisely an adaptive MCMC framework. And if I do everything at once, I will actually generate a simulation that looks more like this, where I'm running local, global training, local, global training. And eventually, I converge to a nice samples that are really distributed as I wish they were. But of course, there is no free lunch. If I was to initialize my local sampler only in one of the modes, there is no mode finding mechanism in this algorithm, and I would just collapse to one of them. So this is really with in mind applications in which you know where are the modes that you are interested in, and you want to be able to recover what's the equilibrium distribution consistently across the bases. Okay, so that's one way to do, and here was just the algorithm that was again highlighted that the procedure is running a non-local metropolis Hastings with proposals that comes from a certain type of deep generative model. And it's true that I didn't give too many names now, that I was a bit in a rush with my introduction as we struggled with the mics. But here, the one I'm using here, I have been using here are normalizing flows, which is just another name of saying that you are going to learn this map that is organized in layers with deep neural networks, and that starts, that are invertible. Let's put it this way. So it's just one of the types of those invertible deep neural networks. Okay, and so you alternate, between this metropolis Hastings with normalizing flow proposals, local sampling, and maximum likelihood gradient updates of the parameters. And so by doing this, you little by little improve your sampler, which improves the quality of the data you get, which improves your sampler, and so on and so forth. So this is again rooted in the literature of adaptive MCMCs. And it also has this taste of this local and mode jumping operations, because here, it's something we've studied to some extent, how much you need this local resampling and how much it helps you. But at least in practice, it's really clear that it's something that stabilizes your learning and your, stabilizing your learning when you do it, and that makes the whole thing more effective. So I guess I've answered a bit to this first point, which is suppose you can train. So I've had some assumption. So either it's a unimodal, or I know how to have a good initialization that covers my modes, or I just know how to initialize one worker in each of my modes. Then I can have different strategies to have a learning objectives that would bring my generative model closer to my target, even if I don't have an extensive data set from which to train on at the beginning. Now remains the question of what does it mean to have rho theta of x close enough to rho star of x? So that's something we are going to discuss a bit. But before, now that I remember, I wanted to mention a few applications, and so something that seems to be well suited for this type of strategy are Bayesian inference in astrophysics, where we are in moderate dimensions. Some models are trying to care about initial conditions of the universe, so you have to have the be in the full dimension of the universe. That's completely out of our leagues. But here, for example, for observation of gravitational waves, they have say 15 parameters that they care about and that they want to fit, and they have how should I say? There is just, time is at stake, because the fastest you can infer the parameters of your model, the fastest you can actually recover a possible location of a possible origin of the signals that you are getting of the gravitational wave. And so the fastest you can try to point more observing more telescopes to the source of the gravitational wave in order to get more data. So when you detect one. And so this is something that one of my collaborators, Case Wong, is pushing, as is an astrophysicist from Flatiron that is really caring about those gravitational wave models. And he seems to be convinced that this is really one of the ways to do things very fast in this type of context.
Sure.
Yeah?
When you say fast, and what sort of time is this?
It's seconds.
Okay.
Yeah. So, okay, so that's one thing. Something else that I'm pushing in the design preparation is looking at sampling of molecular systems. And in this case, we are looking at ab initio computations. So we wish to, if you want, minimize the number of times we evaluate the force fields because it's very, very expensive. We can still use it to run some, seed the program with some initial local molecular dynamics. That's, for example, for these two conformers of 6 atoms of cluster. So 2 of them being stable, and we want to characterize if we run a molecular dynamics simulation for one of them. Of course, we will never have enough compute to observe within this molecular dynamics the transition from one to the next. But here we can use this framework to train normalizing flows to generate candidate configurations, and then have jumps in between the 2 isomers that is here represented. In just 2-dimensional projection of the problem. One of the type of possible applications, yeah.
You use the normalizing flow to propose an initial.
No, to propose at each step of a Markov chain.
If your normalizing flow does not propose you something that has been agreed to within a seed.
Okay, so what you do is that you have some initial data that comes from a local, short local chains, and you can put your normalizing flow to have to be centered around this, and then you refine what your normalizing flow is going to take by only keeping the MCMC data for training the flow. So you will refine, and it will have a better and better overlap with the target. Yes, absolutely. That's again. If that's absolutely, you can. There is no reason you would find a mode. Then you can combine this with other strategies to find modes. That's sure. But here.
Yep. Sorry, you interrupt. So the goal here is to really get the free energy difference in this example, the difference between wells, but not to get, say, for example, the barriers between them.
Exactly.
But just the well.
Exactly.
Okay.
Yeah. So that's a really good point. So here it's something that could give you the information between the 2 wells. And here it's without having to characterize what's in between, or if you can take it as a plus or as a minus, right? Or without characterizing what is between the 2.
Gives you non-physical transitions.
Absolutely non-physical transition. It's the only target is to get the Boltzmann distribution. So if you want, it's yes. So you just want to, as fast as possible, to get equilibrium samples from the Boltzmann distribution at a given temperature. And a third example of what you could try to do with this type of methods is actually training energy-based models. So this is where I hint back to the talk of Beatrice, who showed that you could, that within the problem of energy-based model, you had a sampling problem. And here, let me just spend a few minutes talking about it. And this is work that I've done in collaboration with Louis Greniot, my student who is in the room. But maybe let me give you just a few hints of why we want to do energy-based modeling. So in the case of Beatrice, it's to have something that is interpretable, for example. I can also give a few more arguments. So I think there is this little nice idea about the fact that there is a generative model trilemma, that some of them gives you high-quality samples, or at least the 3 desirable properties of generative models is high-quality samples, fast sampling, and mode coverage density, which is indeed things we have mentioned. And in this ICLR paper of 2 years ago, last year, sorry, what they did is to characterize the fact that some of the generative models, so rational encoder, the normalizing flow, typically have two. So these two, or these two for the denotation diffusion models, or these two for GANs. So if I were to add the energy-based model in the picture, I would say that they also have fast likelihood evaluation and expressivity, and that's really one of also of the things that you may care about when you're doing training EBMs for scientific computations. Is you may want to know exactly what's the likelihood, and for normalizing flows, it's something that can be obtained very fast. But for the arguably more powerful continuous normalizing flows or score-based diffusion model, it's something that is actually quite tricky, and so you might want to instead resort to this energy-based model, which I remind you are the following form, where this time you have a rho theta of x, so a distribution that is parameterized simply as a Boltzmann distribution with a e theta of x that you can choose to be a generic, either RBX, or it could be a very generic neural network, as long as you could in principle normalize this Boltzmann distribution. But as Beatrice has told us, they are hard to sample, and therefore to train, at least if your goal is to obtain a distribution that would really have at equilibrium the same, reproduce really the one that you are after. And this is from data. So here I had just reminded what were the procedure of training, but here I'm just going to go fast. But the bottom line is that in the gradients, if you do maximum likelihood training of an energy-based model, you need to sample from your model itself, and this is where you have a sampling problem. And this is all the more a problem where you have things that are actually multimodal. So when we are trying to model a data set that we have different modes in it, and why am I saying that? It's because we've seen this morning with Stéphane that if we have actually a distribution that is log concave, so sync unimodal, then we could be using something else, which is a score-based method for training, which gets completely rid of the need of sampling from rho theta. So this is true, but this is true if you're log concave. And then it's also true that why is this difficult to sample most of the time? It's because we are looking for a highly multimodal distribution, and so we expect that we have metastable sampling to be done in this computation of the likelihood of the energy-based model. And so the bottom line again is that neither this method is guaranteed to yield a statistically accurate model in model cases, and it looks like you would really need to do a proper sampling in order to get it. So, there is a natural way of thinking of how to adapt those adaptive Monte Carlo with normalizing flows to this energy-based model training. And this would be to have a joint training of an EBM with a normalizing flow that would be designed in the way that the two of them are following one another, such that the normalizing flow can mediate the sampling for the energy-based model, and that you can get the best of both worlds in those trilemmas or quadrilemmas or whatever in this business of doing generative modeling. And so there is, again, it's pretty straightforward to think of the sketch of an algorithm where you would be sampling from the EBM using an adaptive MCMC that uses the flow, and you would use this to compute the gradients of the EBM parameters, and you would use also your samples to compute the gradient of the flow to train everybody at once. Of course, there is a big trade-off that you are training two models, so you really need to have a good reason to be able, to be willing to pay the price of training two models at once. But if this would be the case, then actually there are a few people that have also thought of other variants of combining energy-based model training and normalizing flow and normalizing flows. But none of them were strictly using a sampler for getting the gradients. And so this is why we actually tried to do it. Although now I know that if I only want to generate, I can still have statistical weights. the talk of Beatrice really made this point very clear. But say you want to have a model that gets the at equilibrium, the right distribution, then you would need to really converge this sampling. And here, okay, we have some preliminary results in moderate direction that you can do it this way. And if you have, again, this two-dimensional target, if you are just using Langevin sampler, that would be local in the estimation of your gradients. And for example, that you follow what is the relative weights. So this is the red trajectory as a function of the training for the two weights of your toy bimodal distribution, you would see something like this, that the weights are oscillating. Sometimes one mode disappears, and then it reappears, and then it disappears, and then it reappears. And so at some point it stops, but you don't have any consistent information on what is the relative weights of these two compared to, I mean, in the ultimate model compared to what was in the target. Whereas if you organize to train a flow along the way, you would obtain a final distribution of your EVM that looks a lot like your target. You would also get your companion flow that will be useful in any sampling operation of your EVM. And you would have an estimation of the weights between the two modes that is fairly stable during the training and fairly close to the target. So this is, I mean, one more example of applications that you can think of. I like this is in moderate dimension, but that's, you know, in spirit what you could do. Now, okay, so how do these strategies save to large or complex systems? Because all the examples I've shown you are moderate in dimension. Well, there are a few papers that have tried to sample non-trivial static models with this type of approach and with little success. So there is a nice paper by Del Devio that dates back to 2021, where they look at the scalability of an MCMC that would use as a proposal a normalizing flow trained by variational inference in the case of the 5-4 model. So where you have a phase below the critical temperature, where you are bimodal with mainly so spins that are all up, or a critical phase where things are self-similar, and phase above the critical temperature where things are disordered. And okay, what do they see in their scalability study? They look at, as a function of the temperature, the acceptance that they get in their MCMC moves, again, that are proposed by the trained generative model. And they do this so with color that depends on the size of the training set of the system. So how many systems spins do I have, sites do I have here? So is it 6 by 6 when I have the yellow dots, or is it 20 by 20, so 400 spins, where it's the dark purple dots that corresponds to this line. And so what do they see? They see that the acceptance is going down as we increase the size of the system. And they also see something that seems to be happening at the critical temperature, that corresponds to the critical temperature, where we expect that how should I say, that the landscapes, or actually that sampling is usually harder. So it's what usually we make this statement for local samplers. So here it's not local, so maybe it's not so obvious what's happening, but at least this is what their empirical study reveals. And that should make us pessimistic, because if you cannot sample something that is 20 by 20, maybe, I mean, if you want to, that remains a toy model by many aspects, right? So here your acceptance is going down. It starts to be 30%, okay, still fairly good, but there seems to be this doomed trend to go to zero acceptance, in which case you have spent some time training a generative model that is going to be of no use in your MCMC if everything that the model proposes is never accepted. So, okay, so there's this paper looking at the scalability. There is also, for example, the group of Francesco Zamponi that look at some very hard sampling problem that is the random graph coloring, and that also concluded that this was not so much of a solution. And okay, I mean, fair, that's very, very hard. So there's still plenty of problems for which it's hard to sample, but not that hard, and for which it would be useful, like the examples I gave you before. But I guess it also, I mean, this failure is to be attributed to the fact that actually it's not possible to be in this ideal case where this rho theta of x would be equal to rho star of x, right? Because if that would be possible, then we are done. We just have a model that is easy to sample, that is exactly our target model, and we just sample from it. So it really comes from the fact that there is a mismatch in practice between this learnable model and the target distribution. And this is due to estimation and approximation errors, which we don't know exactly how to disentangle, of course. And again, this is very much at stake because in cases where this is going to anyway be too different, we would have just lost our time trying to generate a model because then we would really have little ways of using it in generative models. So, okay. So this is where you have to read the fine print. So suppose you can train a model such that rho theta is almost equal to rho star, but you get a lot star, provided that the approximation is good enough, which becomes difficult or maybe impossible to achieve for very large complicated systems. So where do we go from here? Well, one key idea is to incorporate some physics in the architectures, and this is something in the way we engineer our interactions between the generative models and sampling, and this is something that Grant or Stefan both mentioned this morning. And here it's just a very simple example that we had put together for the PNS paper with Grant and Eric, where for this same, so 5-4 model, I'm here in 1D, but for the 5-4 model that has the same characteristics as the one we were discussing before, even in the bimodal phase, which here would be, can still be fairly high dimensional and difficult to sample from. What we imagined is, so take the action of the 5-4 model that has so coupling term and a local potential that correspond to having so this double well that makes it that if you look at the equilibrium configurations, so in this 1D model, you have those black lines. So you will go with boundary conditions that pins you at 0 at the first sites and at 0 at the last sites. You would have configuration that fluctuates going from 0 to 0 either through 1 or through -1 with some local scale of fluctuations that are mediated by the fact that you have a coupling term and that neighboring spins tends to be willing to be equal to one another. Well, what you can do is think of a base distribution that will retain everything that you can simulate easily from this distribution. And this is to keep all the quadratic terms and give up on the quartic term, which is giving you the multimodality. And if you do this, you can see that the Gaussian, that you would have a base distribution that is much different from a Gaussian white noise that could have been the default choices in generative modeling. So here, I'm having a lot of black lines that corresponds to a lot of samples of 2 different possible base distribution. So one that is Gaussian white noise. So for each of the spins of the sites, I have completely independent Gaussian draws. So it's just a blob of very much oscillating numbers compared to something that retain the coupling term in from the action of the 5-4, and that actually gives you something with some local fluctuations, but that is still Gaussian, so I can still generate in one go in my computer. And this, for example, was really key to making something work, scale for this 5-4 model. As, for example, for a case where we have 100 sites, as the iteration goes on, we can see the acceptance going up as our flow is training, is getting better and better. And you have, for example, 60% of acceptance for something in 100 dimensions, which is fairly interesting. And you can have, after training, so a generative model that generate configuration that looks a lot like the equilibrium ones. And so that it will be efficient in an important sampling scheme or a Monte Carlo schemes. So that's one example of how you can incorporate physics in architectures, and of course there are other ways of doing it. And another key idea is, of course, to go beyond simple samplers and to combine forces with generative models. So in other way than those two. I have as much? That's, when did we start? Yeah.
8 minutes.
Okay.
Well, so no.
Yeah, okay, well, okay, thank you. And so, yes, it's to, I mean, here again, I started with those two very simple ideas of sampling, of just having a proposal in a Markov chain, or a global proposal in a Markov chain, or having a global proposal for importance sampling. But there are plenty of ways we could try to generate, to use generative models and samplers that are much more sophisticated. And I mean, here I just listed a non-exhaustive list of works that I've started to do things like this. So some preconditioning idea that I may talk about depending on how tired is everybody, or some works using the ideas coming from sequential Monte Carlo, parallel tempering, replica exchange, Hamiltonian Monte Carlo. So a lot of things have started to be explored, and I think there are plenty more, and that could be a topic of discussion for, well, just after this, actually. And so one thing that we've worked on was to look at this preconditioning idea. So maybe I will give you just what's the idea of the algorithm, what's the conclusion, and skip over what motivated me to get this conclusion for the sake of time. But there is another way where we can think of exploiting those learned transport map in sampling. If you want, it's a less greedy way than the one that you do, where you try to make global proposals and refresh all your degrees of freedom each time you make a step in a Markov chain. And it involves the idea of reparametrization or preconditioning. So say that your target distribution is something with complicated geometry. So that's a banana with the tails and some curvature. And you have a base distribution that is just a unimodal Gaussian, so here it's just a tiny blob. Well, if you've successfully trained your T theta, then you will have a way of mapping this simple Gaussian distribution to the push forward that corresponds to almost the target. So here I'm putting the intermediate steps that actually corresponds to different layers that my normalizing flow, because in practice, this is how we make them happen. And so you could look at how your neural network is transporting the mass of the Gaussian towards the target. Now, you can think of the reverse map that is giving you the push backward. And what I'm calling the push backward is something that I can write down explicitly. And that corresponds at taking the target distribution rho star and pushing it through the inverse map T theta. If the training is successful, it should look like the base distribution. Oh yeah, and because there is a, yeah, it should be a rho star. There is a typo I didn't correct here. This doesn't have the base distribution in its expression precisely, but it should represent the base distribution if it was correctly trained. And so, and the idea that I was actually introduced in different papers is to do a local sampling in the push backward distribution. So it's a reparametrized distribution in which you expect that your local sampler will be more efficient because it has all the nice properties of independence of the different coordinates, well conditioning, and that's you should be highly performant there. And okay, and so yes, that's just exactly what I've been saying. And it's a nice idea, and actually we can show. So how should I do it? Yeah.
Yeah, you have a few minutes, please.
So, I mean, no, I think everybody's tired, including myself. So, I mean,
question when you're organizing things.
Yeah.
No, but I mean, if people are interested, they will ask questions. Let's do it this way. I mean, what we can show is actually if you have multimodal distributions, then this preconditioning doesn't work because you actually don't kill the multimodality by the inverse map. And so here we made this little, so in the paper we wrote, again with Louis Grenion, Alain Dirmus and Eric Moulin, and that is in ICML this year. We made this little conclusion, empirical study diagrams, if you want, that for multimodal distribution, actually, you have to, and those algorithms are the ones using the global proposals. So there is no way of taking advantage of this preconditioning because the map you learn in practice are not killing the multimodality. And I can elaborate for whoever's interested. Whereas for unimodal distribution, actually, if you have a very good flow or you are not into high dimension, I mean, the most efficient thing to do is to really make uncorrelated update and to refresh all your degrees of freedom at once. But if your flow is actually quite poor or you're in high dimension, you are better off using this preconditioning that is a bit of a less greedy approach. So if you want, we really made the comparative study of those different algorithms that were proposed, and I think it led to really nice insights that I'm happy to share and happy to discuss with also other variants people would have been interested in. Okay, and so I just finished on these few perspectives for this talk, which is that the progress we are seeing in generative modeling suggests that there is a road to machine learning enhanced sampler. Yet reaching the level of training that is, accuracy that is required is not always trivial, maybe not always possible, I should say. Yet for some cases, for example, Bayesian inference, that will be something quite multimodal or with complicated geometry, for which priors that is in moderate dimension seems to be almost ready-made solution. Physics-inspired architecture should be something we focus on for the physics applications we are interested in, and other interesting direction is really to go beyond the simple samplers and keep on looking at these other things that have been started and that remains to be explored in the possible combinations. And I guess if I put a perspective on this or header to these two last points is really to say, okay, now we realize that machine learning arrived as a new toolbox full of promises, and of course now we are hitting the wall of realizing that we really need to combine cutting edge machine learning with cutting edge whichever other field of scientific application we were interested in order to do anything that is non-trivial and was not accessible by experts within each of these domains. So this is really where we are and where I'm excited to chat with people here. If you are curious about those adaptive sampler and you are a Python enthusiast, then Case and I wrote this framework called FlowMC that is within pip, so you can just install it and look at the examples and play with it. It even has a documentation I need to state. Okay, it has documentation, but we are still open to feedback. We don't pretend it's perfect. With this, I thank you very much.